Alrighty, we got one more. Now, let's just review really quickly what we've learned so far. We've learned that if the first derivative is equal to 0, then I get a stationary point. And a stationary point can be one of three things. Stationary point can be a relative maximum, it can be a relative minimum, or it can be this horizontal inflection point. Okay, we've learned that the second derivative equal to 0 always gives me an inflection point. Okay, now if the second derivative is 0 and the first derivative is 0, then you get a horizontal inflection point. If the second derivative is 0 but the first is not, then it's just a normal inflection point. Now what does the inflection point mean? Inflection point means a change, or delta, change in concavity. Right? We talked about how if the first derivative is positive, that means a positive slope. If the first derivative is negative, then we get a negative slope. If the second derivative is positive, then it's what we call concave up. And if the second derivative is negative, then it's concave down. Okay, now if we put all this together, then we will get the following. Let's go ahead and try one more. Y equals x to the fourth minus 2x cubed. All right, so we go ahead and we're going to take the first derivative. So we're going to say y prime equals 4x cubed, right? You bring the 4 in front, subtract 1 from the exponent, minus 3 in the front, so 2 times 3 is 6x squared. All right, now at this point, if I want to be able to get some information, create a sign diagram. For the sign diagram, I want the x-intercepts of the first derivative. Now remember, this sign diagram is for f prime of x, or y prime. So I'm going to go ahead and set it equal to 0. So I'm going to say 0 equals, and then it looks like I can factor out a 2x squared, which will leave me with 2x minus 3. And that means I'm going to have x equals 0. Notice that's an x squared, so this one is a double root. And then if I add 3 and divide by 2, I will get x equals 3 over 2. So those are going to be my two x-intercepts, my critical values here. So 0 and 3 over 2. Now what happens to the first derivative if I put a really big positive number there? Well, of course, it's going to end up being positive. Now, because this is a single root, it should alternate there. And then to the left, because 0 is a double root, it should not alternate. If it's an even root, then it should not alternate. It should just stay the same. Now, just to double check, if I were to put negative bajillion there, a negative bajillion cubed would end up giving me a really big negative number. Now, that really big negative number, even though this one right here, well, as you see, you're going to get minus another number. Negative bajillion squared is going to be positive, so I'm going to subtract a positive, a negative minus a positive is going to give you a bigger negative number. And so we end up with a negative number no matter what over there. So we now have something like this, where the derivative is negative before 0, and then at 0 it's flat, right? 0 is a stationary point. Okay, then the slope is negative after 0, which means that it continues to go down. At 3/2, it's stationary, and then after 3/2, the original function is positive. Now remember, what I'm drawing in here, the blue, is a sketch of f of x. So I'm getting an idea of what f of x looks like by knowing what the values of the derivative are. The derivative, the slope is negative, it goes down. At 0, remember at 0, the derivative was 0, and that's why it's flat there. Now, what we notice then is that at x equals 0, I have a stationary point which is not a maximum or minimum. So that is a horizontal inflection point. Okay? Now, at 3/2, when x equals 3/2, That's negative before and positive after, which means I have a relative minimum. Okay, now I go on to the other one, and we're going to go ahead and do the second derivative now. And if I do the second derivative, then I will take the derivative of this one right here. So the second derivative, y double prime, will give me 12x squared, and then bring the 2 in front, so that would be minus 12x. I factor out the 12, x, leaving me with x minus 1. So therefore my critical values will be at 0 and 1. Now if those are my critical values, then I can find positives and negatives. Let's see, if I put a really big positive number in, again I'm going to get positive there. If I put in something between 0 and 1, well, it should alternate, so hopefully it goes negative and positive. Just to check, if I were to put a really big negative number there, again, if I put negative googolplex there, it'll be positive because I'm squaring it, and then put a negative in here. The negative times the negative is going to be positive, so I'm going to end up getting a positive anywhere to the left of 0. Therefore, it is going to alternate just like that, and so that looks good, plus, minus, plus. So what does that mean? It means before the 0, I am concave up. After the 0, I am concave down. And then after 1, I am back to concave up. Now, notice that at 0, I have a stationary point, which means it needs to be concave up. Before that, there is no stationary point. Okay, so the graph isn't going to be a full concave up like this. Alright, what that actually means is it needs to be concave up before the 0, but it needs to not have a minimum. And so that means it's got to have some kind of concave up like this. Okay, or it could be the other half. It could be something like it's got a negative slope. So because it's a negative slope and concave up, that means it probably looks like this. Alright, that's concave up. That's the first half of the concave up graph. Now we look at concave down. So after 0, it's got to be concave down, and it's still a negative slope. So concave down, negative slope will look something like that, right? And so we've got concave up, concave down right here. So concave up, concave down. Right there in the middle, we do have our horizontal inflection point, which is what we said we would have at 0. Now this is concave down. At some point at 1, I'm going to change to concave up, okay, which means it's going to go from there and it's going to go concave up, which we note then at 3/2 is where we're then going to get our minimum value down here. So we're going to get our minimum value. Notice at 1 it changes from concave down to concave up. Okay, it doesn't change from a negative slope to a positive slope. It changes its concavity there. Okay, now just as one final thing, we should recognize that from negative infinity up to 3/2, the graph is always decreasing. And now sometimes students are a little bit confused. They say, well, what about at the 0? The slope there is 0. Okay, well, that's true. The slope at 0 is 0. But it's important to notice that any point to the left approaching 0 always goes down. And if I were to go from 0 to another point, it's also going down, which means over that whole interval, it's decreasing. It's going down. So we would say that this graph is decreasing from negative infinity up to 3/2. And we would include the 3/2 because, again, everything approaching 3/2 is going to be negative. Where is this graph increasing? Well, everywhere after 3/2, because the slope is always positive. So again, we're going to include the 3/2 because if I start at 3/2 and go just a little bit to the right, I've gone up because the slope is always positive there. So this graph is increasing everywhere to the right, including 3/2, 3/2 and everything to the right. Okay, so using all this information, we can get a little bit better idea of what our graphs look like, regardless of what the type of function is, a quadratic, a quartic, a quintic. It doesn't really matter. We can get a better idea of what these things look like now just by using derivatives. And we can prove whether points are horizontal inflections or minimums or maximums. And we have two ways of doing that, both with the first derivative and with the second derivative. All right, that is all.